discuss about design of gating system in sandblasting. Therefore, first let us see first what are the elements of gating system. Now this is the mold, green sand mold. Now here we are having, this is the actual cavity, mold cavity, and these are the different elements of the mold, and in this we are having the pouring basin, sprue, or this is the sprue or down sprue, a runner, gate or in gate, this is a gate or in gate, or riser. Over here a riser is there, and these are the elements which we call the gating system. Now therefore design of pouring basin. Pouring basin at the top, from here we pour molten metal in the pouring basin, so much so that there should be there should not be a vertical flow, and only the vertical flow should take place, and no horizontal flow should be there, and try to minimize, reduce, or eliminate the laminar, the turbulence flow. And therefore now with that we need to pour metal in this pouring basin. From there it will start flowing to the mold cavity, and we can, in some cases, mostly in the low density material, we provide a skim core or a skim bob, so that some slag or dross floating on it may not get into the basin, and it may be properly filtered, and only the pure molten metal should go into the sprue and then to the cavity. Now when the metal flows in the cavity, then the absorption of gas from the surrounding takes place by the molten metal, and therefore during its flow the aspiration effect is in the down sprue, and that can be avoided by fabricating tapered screw, or it can be in the runner. It can absorb gases from the surrounding, but therefore this can be avoided by having a laminar flow. Similarly, in mold cavity, it can absorb gases, and that can be again achieved by having laminar flow in the cavity itself. Now therefore, while designing a down sprue, first of all we know the Bernoulli's theorem. This is the top of the down screw, and this shows the bottom of the down screw, and the top is exposed to the atmosphere, while cavity is also exposed to the atmosphere. Therefore P1 is equal to P2, and that is atmospheric, and we also ignore the friction force. Thus this becomes H1 plus V1 square upon 2G, H2 plus V2 square 2G, and therefore the difference in the pressure will give to calculate the difference in the velocities between the 2 points. Now therefore designing also, now from continuity equation we know the flow at the top and flow at the bottom should be constant, and that can be given by the area at the top and the velocity at the top. Similarly, area at the top and the velocity at the bottom and from the Bernoulli's equation we have already seen that this Vi depends upon the depth of the location from the top, and therefore we can find out the velocity at a particular depth in the sprue, and therefore the area at the top and bottom can be related. Now this equation shows a parabolic equation, and therefore the area at the top will be inversely proportional to this and to the square root of the depth or the height from the top, and can be calculated. Therefore, we can calculate the at different height or different depth, we can calculate the area, and generally it is obvious that tapered one will give a good compromise with the equation and avoid uh, aspiration effect. Now, another terminology which generally we use in getting system, which we call getting ratio. Now, this is ratio between the cross-sectional area of the bottom of the downspout, cross-sectional area of the bottom of the downspout, and cross-sectional area of the runner, and the cross-sectional area of the ingate. Now, if the area of the down sprue is known and getting ratio is known, we can calculate the cross-sectional area of the runner and the cross-sectional area of ingate. Now, it can be this getting ratio can be pressurized one when the cross-sectional of the bottom of the down sprue is more than that of the cross-sectional area of the ingate, then the velocity in the ingate will increase, and therefore that due to this we call it a pressurized one, and that can be used for low density material so that it can fill each and every corner of it. However, if it is the cross-sectional area of the bottom of the down sprue is less than that of the cross-sectional area of the ingate, then this is non-pressurized, and the velocity entering into the cavity will be low, and turbulence, if any, can be stopped, and that generally it is being used for heavier metals. Now, what is riser? Riser is a reservoir in the mold and a source of liquid metal to compensate liquid shrinkage. What happens that the molten metal is poured in the cavity at a superheat than the solidification temperature. Therefore, while from superheat to solidification temperature, not only this, during solidification phase change shrinkage takes place, and during phase change even there some liquid is there, and therefore flow of liquid is can be achieved, and therefore what we can do, we can provide a feed mechanism so that during this liquid shrinkage the proper feeding of the molten metal should be given to the cavity so that we can have a defect-free casting. Now this is the actual main cavity for the casting, and this gives a top riser, which is the top of the cavity, while it is at the side of it, and therefore it is known as, and therefore the volume of the riser should be sufficient so that it can feed all the liquid shrinkage and compensate all the complete liquid shrinkage, and therefore properly designed. And therefore, however, the type of riser can be a top riser or side riser, or can be an open riser, or can be a blind riser. Now, here we are having a side riser, but it is a blind one because it is covered by the sand. However, in this case, in this figure, this is a mold cavity. Same type of casting is required. It is having a top riser, but it is open to the atmosphere, and we call it an opener. Therefore, it is open type top riser, and this is blind type side riser. Now, therefore, now we need to design a riser. Now, if the length of the solid pattern is known and width of the solid pattern is known, and similarly thickness of the solid pattern is known, therefore there can be suppose a cylindrical hole in the face of the through hole between the face of the pattern with a diameter of d, and therefore the volumetric liquid shrinkage, the coefficient of volumetric liquid shrinkage is suppose x, and therefore we can find out the total volume shrinkage of the molten metal, which can be given by this particular equation. This is the volume of the, this gives the volume of the cavity of the molten metal required in the cavity, and x is the coefficient, and therefore this gives the volume of shrinkage. But therefore the volume of the riser should be sufficient enough so that there may be there should be a sufficient supply of molten metal in the cavity, and therefore it is 3 times of the shrinkage which is required by the molten metal in the cavity, by the metal in the cavity. And therefore now we need to design a top riser. We know the volume of the, this is equal to that total shrinkage, 3 times of the shrinkage taken place, and this dimension, this gives the dimension of the riser, and that can be related, this S can be related with, because this is VR is constant that we need, as we have already seen how to, what is the amount of material in the riser, and therefore this can be related, the height and the diameter of the riser can be related to each other, and therefore we can find out the surface area. Only the top riser, only the top surface will expose to the atmosphere, and there will be heat transfer, and the curved area will have the heat transfer. Therefore this will give the surface area in terms of the volume of the riser and the diameter of the riser, and therefore now we can differentiate it and equate it to 0, so that we can have an optimum value dimension, and therefore we can see that this is height is equal to diameter is equal to twice that of height, and it is equal given by this particular equation. This dimension is the optimum dimension which with the volume that we need, that of the riser. Now similarly we can design a side riser. We know the volume will remain same, but the side riser will have top and bottom surfaces, and therefore surface area will be twice of the area of the face, of single face, and therefore we can have the equation, we can replace this H with respect to VR, having the particular equation, and differentiating it to 0 with respect to D, differentiating to 0, and we can find out the value of the dimension, diameter is equal to height, and it is given by this. This is the optimum dimension of the riser. Now we can also calculate the solidification time. Now solidification time depends upon the volume of the molten metal. More will take more time to solidify, less will take, therefore directly proportional, but it is inversely proportional to the surface area. Okay, higher surface area will reduce the solidification time, and therefore that can be, this proportionality can be given by this equation. Now for sand molding, we assume that this gamma is equal to 1 and n is equal to 2, and therefore the equation will be written for sand molding. We can have the, therefore we can calculate, if the volume is known and surface area is known of that of the casting or the riser, we can calculate the solidification time of in the riser as well as in the cavity. But one thing very important, that solidification time in the cavity must be less than the solidification time in the riser, then only the riser will be able to, if solidification time in the riser is more, then only the riser will able to feed liquid material to the mold cavity. Otherwise, if it is earlier, prior than that of the cavity, then of course it will cease to supply the molten metal to the cavity. And therefore filling time, we know the volume of the cavity and mold cavity, and we also know the flow at the in gate, and therefore we can find out the filling time. But one thing very important, that filling time should be a small fraction of the solidification time. That means the metal should not solidify prior to filling of the cavity. Its filling solidification time should be sufficiently high than the filling time. It should be first each and every corner of the cavity should be filled, and then solidification of the of the molten metal in the cavity should start. And therefore, safely we can have approximately 10%. If we know the solidification time, we can calculate the solidification time in the cavity, and it should be 10% of the solidification time. That gives us sufficient the amount of time to fill the. Accordingly, we need to design the gating system. And empirically, we can also calculate the pouring time for grey cast iron, for steel, for ductile iron, for copper alloy. However, the pouring time for non-ferrous material is longer, since they lose heat slowly, and also to avoid dross. This K1 and K2 in the previous equation can be taken from this particular table, and therefore this is the equation which we need to solve, so that we can incorporate all the allowances in the pattern. This is the product we need. This is the casting product that we need, with the length, width, and thickness, and the through hole. Now we need to design a solid pattern, split pattern, top riser, side riser, and gating system of the for this pattern. Therefore, thank you for hearing and giving time to